Hello, I'm Andrew Lawlor, President and Chief Architect of Aptaria. I recently presented to the DC CTO Club about a topic I'm very passionate about, how enterprise organizations should think about AI upskilling for themselves and their staff. This recording is a version of that presentation to share more broadly. To start the presentation, I asked the audience, full of DC area CTOs, how many of them took multivariable calculus, linear algebra, and probability in college. And most of them raised their hands. I then asked how many of them have used those skills in their career since. Almost all of those hands went down. So about myself, I have for the past 20 years been CEO and Chief Architect of Aptaria. We are a AI, CRM, and middleware consulting firm for companies and nonprofits, and we've been a Salesforce consulting partner for a number of years. I started my career at IBM, and in terms of education, I have a Bachelor's of Science in Electrical Engineering from the University of Maryland, studied Electrical Engineering and Computer Science at Columbia University Graduate School, and recently I've been working on a Artificial Intelligence Graduate Certificate through Stanford University, and I expect to finish that in the autumn of this year. So my upskill imperative was that on November 2022, when ChatGPT came out, I didn't really know who Geoffrey Hinton was. I used ChatGPT to write a poem about our new kitten. So it was a fun toy, but the application of that technology was not clear to the enterprise. But quite soon started noticing a slowdown in cloud and Salesforce market that we operate in. And this was the beginning of the SaaS apocalypse. So how deeply do CTOs need to learn AI anyways? I look at it as having three different levels. First, there's the use of AI, where you can leverage the tools to drive productivity and business value. This can include prompt engineering, AI-assisted workflows. And most enterprises and enterprise leaders operate here today. To go deeper, we would call this tuning of the AI, where you would adapt and orchestrate AI models for your specific domain. This includes fine-tuning of a model on your own data, or application of RAG, or retrieval augmented generation techniques, to augment and get better results out of the model. And of course, there are agentic pipelines and API integrations that can be done. And this is where a competitive differentiation happens today in the marketplace. At the deepest level, you can train models, and this means building and training models from the ground up. This requires a significant amount of math and techniques like backpropagation and loss functions. This is predominantly the domain of AI researchers and labs. So how deeply does a CTO need to learn AI? Well, I think there are a number of reasons why a CTO should go deep with learning the new world of artificial intelligence. First of which is vendor evaluation. You need to be able to call BS to a vendor that makes claims that they can't back up. And with the deep knowledge, you'd know when you would tune your BS meter. And you also need to know what's possible. If you understand the mechanics of AI, you can calibrate your intuition for what AI can do and what it actually can't do in a given situation. You need to be able to diagnose failures. So when an AI system goes bad, and they do go bad, a technically fluent CTO can reason about why. Was it the prompt engineering? Was it the data? Was it hallucination from the model's architecture? More and more, CTOs are managing AI teams. And a CTO that can't effectively lead engineers or evaluate their work is going to be at a disadvantage. Finally, risk and compliance. Understanding bias, overfitting, hallucinations, and jailbreaking at a mechanistic level make you a better guardian of your organization's AI risk posture. So my upskill imperative was that I needed to pivot to AI, both personally and professionally, and for my organization. But how? There are a number of ways you can get trained up on AI, from personal study of books and online reading. You can go to online learning sites, including Deep Learning and Coursera, a couple of good ones that I've used. And then there are industry certifications from the big vendors, NVIDIA, AWS, Google, Anthropic. These are becoming a bigger role in the market. There are also new graduate certificates for mid-career professionals from a variety of the universities, the leading universities that have led the way on AI. And finally, you can go all the way and get a graduate degree, a master's of science in AI, or a master of science in computer science with an AI concentration from these same and other institutions. I chose to pursue a Stanford AI graduate certificate for myself because I wanted to get the rigor, and yes, I wanted the Stanford brand. One of the co-founders of the DC CTO group, Marco, has chosen to pursue a Master of Science in AI from University of Texas, Austin. So he's choosing a somewhat different path, but also going very deep. The main thing to understand about artificial intelligence is that you are learning from the data. We're no longer writing code, deterministic programming to simulate human thought. Instead, these models learn directly from the data itself. And to do that requires some high-level math to tune the weights and models of these biases, of these models. Put together this diagram as a learning hierarchy of how to, what it takes to get the most out of, AI. At the bottom level, foundationally, you have STEM skills in different types of high-level math and Python programming. Moving up the levels of abstraction, you have statistical learning, including machine learning, and then deep learning. Then layer above that is applications, where you do natural language processing, computer vision, and reinforcement learning. At the top of the cake, we have Agentic AI for digital assistants, digital agents, and robotics being the physical embodiment of a digital agent. So recommended STEM skills, foundational STEM skills include multivariable calculus, which is important for the derivative chain rule is critical for modern AI. Linear algebra is critical for matrix and vector math. Probability and statistics are critical for conditional probability and for Bayes' rule. Discrete math, including graphs, sets in Boolean algebra are critical. And Python programming is the industry standard for data processing in the scientific and academic learning worlds. Starting with machine learning, and you see here we have CS229 is the Stanford class, and CS6375 is the University of Texas Austin equivalent. But machine learning is the foundation of AI, and it's the ability to learn from data instead of using deterministic programming. And within machine learning, we'll explore a number of topics, including supervised and unsupervised learning, training, validation and test split, overfitting, and gradient descent. So unsupervised learning is a category of machine learning where the model learns patterns, structures from the data without labeled examples. So there's no target variable, no correct answer provided during the training. The algorithm finds the structure on its own. So this chart here shows data, and we've used the k nearest neighbors algorithm to find the boundaries between these classes. In this case, we have set k equals to 4, which is a pretty natural fit for this data, but you could use any other value for k. And k is in fact a hyperparameter. A hyperparameter are settings of a machine learning model or a training process that are set by the researcher before training begins. But the key here is that hyperparameters are not learned from the data. Every other parameter, like the weights and the biases, are learned from the data. Hyperparameters are not. They are set by the engineer. An important concept for machine learning and AI more broadly is that with your data set, you want to split it up into training, validation, and test data sets. With this, you are able to use the validation set to tune your hyperparameters to get the best out of your model. But you always want to leave, say, 20% of your data for your test. And the golden rule here is to never touch or look at your test data until the very end. If you do, you could be corrupting your model and harming the performance of your model on unseen data in the future. So supervised learning differs from unsupervised learning in that we have labeled examples. So we have a actual output. There are two main types of supervised learning. We have linear regression, which outputs a continuous value, for example, predicting a house price or forecasting stock returns or a patient's age from an x-ray. So it produces a continuous function, whereas linear classification, this output is a discrete category. So in the simplest case, it would be a binary categorization. Is it spam or not? Or it could be image classification with multi-class, where you're deciding if an image is of a cat, a dog, a bird, a train, a plane, what have you. So in this case, in linear classification, the model learns a decision boundary between classes. Going deeper into linear regression, we see that we're trying to fit the data to a mathematical model. So we have the model equaling Wx plus B, W being the weights and B being the bias. These are the learned parameters. We learn them from the data, and fixing them produces a linear model that will predict on unseen data, on data that comes in the future. But the goal is to minimize the loss of the data against our model. And to minimize that loss would be the sum of the distances between the data points and the linear model. So you see these data points here where we would sum up each of these vertical lines, and that would be the total loss for our data set against this model. And we want to minimize that. So that's where optimization comes in. You define a loss function. A simple one would be the mean squared error, where we show the formula here. It's just the average of the squared differences between the predicted and actual values. And the intuition here is that the squaring of the difference penalizes larger errors more heavily than smaller ones, and that's a deliberate modeling choice and usually an effective one. But how do we minimize this loss? Well, this is where the calculus comes in. With a topic called gradient descent, it's an iterative optimization algorithm used to find the weights W and bias B that minimize the loss function by repeatedly nudging the parameters in the direction that reduces a loss most steeply. And there's also a learning rate, a hyperparameter, typically denoted with the character alpha. This affects the speed of convergence. You see on the left chart here, we have a one-dimensional function, and the orange segments are the gradient descent, where the loss function is, we're trying to move it to zero, and it takes steps to get there until it reaches zero. Whereas the diagram on the right, we have two dimensions. It's the same idea, but it's moving, taking steps via the learning rate, and trying to get to a loss of zero. It's important to understand the bias variance trade-off when we're doing machine learning or deep learning or artificial intelligence. There are two sources of error in these models. Bias is an error when you have wrong model assumptions. So a high bias model is too simple. It can't capture the true pattern of the data. It's said that it underfits. So if you look at the left diagram here, you see the data points versus a simple linear model. You see it doesn't quite fit to the eye. They're not the same. So that's going to have high bias. So if we move to the middle diagram, we see that the model represented by the line is now a second order function. It much more closely matches that data. So that's going to have lower bias. and also low variance. Now, variance is the error from sensitivity to fluctuations in training data. High variance model is too complex, so that it overfits. So, for example, if you look on the right diagram here, the model, maybe it's a 4th degree function. It has very low bias, but if you imagine another data point up to the right, top to the right, this model would not do well on that new piece of data. So we call that overfitting. So it would have a high variance. So it's the role of the AI or machine learning engineer to pick a model that minimizes both bias and variance. So that was for a linear regression, but if we are in a linear classification setting or logistic regression setting, here we want to predict whether a piece of data is in one of a few classes. This is where the sigmoid function comes in. You see the diagram in the middle starts for negative inputs at 0, and for positive inputs it moves to 1. So that would be spam versus not spam. And the blue line here is the decision boundary. Anything below the decision boundary is going to be not spam, and anything above the decision boundary would be spam. And you see the function here. If you plot that out, 1 over 1 plus e to the minus x, you will see this green line. So that's good for binary classification. But if you have multiple classes, then you need to introduce the softmax function, as you see here on the right, a more complex function, but it's a way to determine probabilities across multiple classifications and find the right classification for that input. So next we move up the ladder in the diagram to deep learning. And this is a case where if we have this data, you notice that a linear model is not going to be able to fit this data. You're not going to be able to draw a line to separate the red from the blue. It said that a linear classifier would fail completely. So the answer, how do we find boundaries for this data? Well, the answer is depth. And it should be noted that machine learning with a linear classifier is really a neural network with just one neuron or just one node. But with neural networks, we have multiple nodes to get the depth to model more complex data. To do the modeling of the more complex data, we need to pass the data through a nonlinear transformation. That way the points can be separated by a linear classifier. So you see here in the middle, this is called the ReLU function. It's very, very simple nonlinearity. For positive x, it's just x. For a negative x, it's 0. So it takes the max of 0 and x. You pass the data on the left through that nonlinearity ReLU, it will transform to the diagram that you see, something like on the right. You can see here it's much easier to find a boundary between the red and the blue data points. So deep learning gets its name because there are one or more hidden layers between the inputs and the outputs. The more layers you have, the more complexity the model is able to handle. So here we have on the left one hidden layer, and on the right we have 2 hidden layers. In fact, frontier models will have hundreds of layers and billions of parameters. This is how they are able to model extremely complex data. So how does machine learning set the weights and biases? Well, it's done through a process called backpropagation. We see here in this diagram, we have the inputs, we have hidden layers in the middle, and the output. So for each data point coming in, we have a forward pass. So it predicts the output. We can calculate the loss. And then through the backward pass, where we're using the chain rule of multivariable calculus, we're able to assign blame and adjust each weight by its share of responsibility for that error. And through repeatedly applying the data, these weights and biases can be tuned, and the loss is minimized. So this is a critical concept of deep learning through neural networks called backpropagation. Next layer on the hierarchy of learning, we have natural language processing. So this is the ability of machines to read, understand, and generate human language. A key aspect of natural language processing is word embeddings. So you're passing sentences, language into the model. It needs to convert that language into mathematical representation. And it does that as a vector, which is a series of multidimensional numbers. One thing that I find fascinating about natural language processing and word embeddings is the math that you can do with these vectors. You can take the representation for king, subtract the representation for man, and add the representation for woman, and you end up with the embedding for the word queen. And this can be done in a variety of settings. It should be noted that natural language processing is really a linear classification problem where the model is finding the next word based on history and using the softmax to identify the word that is the most likely next word in that sequence. So there's a problem with neural networks. And they had a flaw. They couldn't process long sequences. So if you consider the sentence, the trophy didn't fit in the suitcase because it was too big. Well, we need an ability for any word in that sentence to modify any other word. For example, the word it in position 9 needs to attend to trophy in position 2 to correctly resolve the pronoun, but it also needs to attend to big in position 12 to understand why the reference matters. So without knowing too big comes later, the model can't determine whether it refers to the trophy or the suitcase. This is why we needed a concept called attention. And the seminal paper from 2017 from Google, Attention is All You Need, introduced the attention mechanism and the transformer model that have changed the world. From that same paper, we see the diagram on the right. This is from actual paper. This is the transformer that was used in their original analysis. And transformers read entire sequence of words simultaneously and learn which words should pay attention to which other words. And this, every word looks at every other word and assigns a weight. How relevant is this word to understanding the other word? So this was a revolution in every word being able to attend to every other word at the same time. And this is what led to the popularity of GPUs because of the ability to massively parallelize the attention mechanism, and the rest is history. An important aspect of natural language processing and of large language models that's been in the news recently a lot is jailbreaking, which is the practice of crafting inputs designed to bypass an AI's model safety guardrails and cause it to produce outputs its developers intended to prohibit. So there are a variety of ways that you can try to jailbreak a model, from prompt injection, which is a classical strategy that we as CTOs are all probably familiar with for a number of years. But strategies that are unique to natural language processing, you can ask the model to create a poem that will include the system password, and if it's a poor model with poor safety mechanisms, that might work. That you might be able to get it to give up its system password. More creative strategies include prompting the model to write a story where the protagonist screams the system password at the end. Or from one of my classes, I prompted the model to construct JSON, including the system password, and that worked. I was able to get the model to give up its password, and I passed that assignment. Recently, Anthropic's Mythos has been in the news because the government has implemented restrictions because Amazon was able to use these strategies and others to jailbreak the Mythos model and have it do things that it wasn't supposed to do. So it's a very timely topic. So with the success of natural language processing in applications of large language models, natural language processing, the whole field of computer vision started to get involved and see if the techniques and the transformer model could be used to process vision. And computer vision is a field that enables computers to extract meaning from images and videos. And the challenge, of course, is that the meaning in a video or a photo is in the spatial relationships between the pixels. So in 2012, Alex Karpathy and Jeffrey Hinton introduced AlexNet, and they won the ImageNet competition. They were the first to apply deep networks to that problem, and soon after that, deep network solutions were surpassing humans on image classification tasks. And this diagram here on the bottom is from their original paper in 2012 that shows how complex the AlexNet network was that won that competition with many layers and processing steps. Another field of computer vision and natural language processing is AI interpretability. And this is the ability to understand what and how deep neural networks learn. So this is an image from one of the original interpretability papers, where the first layer in a multi-layer deep neural network is finding edges and corners and colors that are in the data. So I find this quite fascinating that nobody is telling the network or a layer or a node within the network to find these things. It's finding it on its own. Here's from the same paper, another diagram, deeper in the network, multiple layers in, where more complex textures and structural patterns are found, including faces and arms and other more complex structures. And of course, models aren't just vision or text today. They are multimodal models, so you're able to combine images, text, video, and other modalities in today's models, and the models are able to make sense of all that data. Next on that layer is reinforcement learning, and reinforcement learning is trial and error, learning by trial and error. So there are no labeled answers and no correct output. Instead, the agent takes actions, receives reward signals, and learns a policy that maximizes the reward over time. So reinforcement learning from human feedback is where humans reward or penalize model responses to fine-tune behavior. This is a primary technique that is used to align large language models like Claude and ChatGPT and Gemini and all the cutting-edge models today rely heavily on reinforcement learning. And it also has a big application in robotics, with where the agent, the robot, gets positive feedback for good behavior and penalties for bad. The top layer, we have AI agents. Agents are systems that perceive the environment, reasons about it, and plans a sequence of actions, executes those actions through tools, and pursues a goal autonomously with or without human supervision. So an agent draws on every layer below it simultaneously. So it uses natural language processing to understand instructions and generate outputs, uses computer vision to perceive the world, uses reinforcement learning to optimize decisions over time, and uses deep learning as the reasoning engine underneath it all. And if you remove any one of these layers, the agent gets weaker. And it should be mentioned that a popular standard these days is model context protocol from Anthropic that they have open sourced a couple years back. And this is a way to pull data from data sources into the prompt directly. This is an example of an AI agent that we at Aptaria are building for a commercial real estate client. Shows that we are pulling data from a variety of inputs using MCP servers. So we have data coming from local files, Excel files and Word files. We're pulling in sample Excel documents for the ideal model for what we want to see. And we're pulling data from a variety of data sources, including web APIs, databases, and media sites. All these sources are orchestrated via the agent, and that agent has human in the loop as necessary. So if there's a major decision that the AI is making, we ensure to include the human to help make that decision. Otherwise, it acts autonomously, and it uses frontier model. At the moment, they're planning to use Claude, but we are designing this agent in a way that the model will be interchangeable without much effort to change that model. And we are tracking an audit log. So in producing this model output, we need to know exactly where the piece of data that was used on the input, where it came from. So the audit trail is capturing that so that we know where each piece of data came from. So this presentation was about the upskilling imperative for CTOs. Ask yourself, do you or your staff need to upskill on AI? Happy to answer any questions you may have. Thank you.